Having developed all the machinery for describing rigid body motion, that is the angular momentum, change in angular momentum, its relationship with the torque applied and the conservation of angular momentum, now we are ready to apply this machinery to rigid body rotation. We start with simplest of the problems in rigid body rotation, and that is the motion of a rigid body about a fixed axis in space, and for convenience I call it the z axis. The only relevant parameter in this is going to be how much does the body rotate about this axis, because the only thing I am considering is rotation of this body about this axis. So, all the relevant quantities are going to be rotation, about the axis, and component of angular momentum along the axis. Any other component of angular momentum, even if it changes, is sort of compensated for or balanced by the torques applied on the axis to keep it fixed in space. So, right now what we are considering is really the axis is fixed in space and body is rotating about it. I am not even allowing for the axis to translate, that we will consider the next step. So, we are considering a fixed axis rotation with no translation. As I said, other components of angular momentum in this case are compensated for by the torques that I apply to hold the axis in place. The only component is the component of angular momentum along the axis. So, let us first calculate that. So, let us take this as the z axis, this as the x axis, this as the y axis, and the body is rotating like this. Since L is a vector quantity, I also need a convention for its sign. I will take the right hand rule, that is, if I point my thumb in the direction of the axis, the direction of fingers curling give me the positive direction of omega and L, and the other way is going to be negative. So, this way is going to be positive omega and the other way is going to be negative omega. Same thing with Lz, same thing with Lz. So, let us calculate L by definition. Lz is going to be summation I mi Ri cross Vi z component, which is going to be equal to summation I, where I really refers to different points, different masses on this body, mi x I V I yth component minus y I V I x component by definition of the angular momentum. Now, let us look at any point, ith point moving. It is really moving in a circle about this axis. This, as I said earlier, let this be the x axis, let this be the y axis. So, velocity v at any given point is in this direction, phi direction. Recall your planar polar coordinates, and r is obviously in r direction. The magnitude of the velocity, let me make the figure again. This is the rigid body rotating, this is point I is really moving in a circle like this, with this magnitude of the velocity being r, where r is this distance omega. The x component of ith particle is going to be r I cosine of phi, y component is going to be r I sine of phi. Velocity is in phi direction, and therefore, ith particle x component is going to be equal to omega r I sine phi with a minus sign, and V I y is going to be omega r I cosine of phi. Recall, Lz is nothing but summation I m I x I V y for ith particle minus y I V x for the ith particle. Substitute all these quantities in. This is going to give you r I square cosine square phi, and this term is going to give you r I square sine square phi with a minus sign. So, minus minus will compensate, and therefore, I get Lz for this body which is rotating about the z axis with omega as summation m I r I square omega, which I can write as summation part inside m I r I square omega, and this we call the moment of inertia. About the z axis. So, let me call this I z omega. This you have seen in your 12th grade, but now I have given you a rigorous derivation starting from the basic definition. I z is nothing but mass times the perpendicular distance from the axis. Remember, r I is this. It is not the distance from the origin, but the perpendicular distance from the axis. Multiply m I times r I square, add it up, that gives you I z, times omega is L z. So, what we found is that given a body which is rotating about an axis, its angular momentum L is going to be given as I omega. I have dropped the axis z, where I is nothing but summation m I r I square, where r I is the perpendicular distance from the axis, or if the mass distribution is continuous, I can write as d m r square. Again, the sign convention is going to be, if I take my thumb in the direction of the axis of rotation, then this curl finger gives me the positive omega. I mean, the thumb is pointing in the positive z direction or positive direction, whichever I choose, and the other way gives me negative. Remember, L is a vector quantity. So, this is equivalent to, when I talk about one dimensional motion, momentum which is a vector quantity could have negative or positive values depending on which way the particle is moving. So, now with this I am now going to illustrate a few things regarding angular momentum, considering this definition of L about a fixed axis. Having discussed angular momentum, now I am going to illustrate how angular momentum really affects the motion or rotational motion in different situations. As a first example, I take this platform which can be freely rotating. So, if I stand on it and start rotating, I will have an angular momentum about the axis. I will show you first the effect of how changing the moment of inertia changes my angular speed in order that the angular momentum remain constant. So, let me stand on this platform, push myself slightly so that I start rotating, and I will take my hands out. You see, I have slowed down. As soon as I take my hands in, I will start moving again. So, let me show it to you again. I rotate myself. As soon as I take my hands out, I slow down. I bring them in, I start moving faster. Maybe the effect is not visible to you because my hands going in and out may not change the moment of inertia so much. So, I have taken two weights to increase my moment of inertia if I move my hands in and out. I will repeat the experiment, and this time the speed change should be visible to you. I stand here, I am not yet rotating, but I want to show you, if I take my hands out, since these masses move out, m I r I square for the masses would increase, the moment of inertia would increase, and therefore the speed should go down if the angular momentum has to remain constant. So, let me rotate myself and I move out. You see, I have slowed down. As soon as I take them in, I move fast. I take them out, I slow down. I take them in, I move very fast. So, this is an effect of conservation of angular momentum. I will in a minute explain it again on the screen, but now let me show you the effect of changing the masses. Now, I will take, instead of light masses, two heavier masses, and you will see that the effect will be much more dramatic, because as I take the masses out or in, because they are heavier, the change in the moment of inertia would be much larger. So, let me do it again for you. I stand here, take my hand out, and I am moving slowly. As I come towards you, I will take my hands in, and you will see I am moving very fast. Again, I will take them out and I start moving slowly. As I put them in, I move very fast. You see the effect of conservation of angular momentum and the change of moment of inertia. Let me explain this on the screen. What we did was, I was standing on this platform which could rotate. Let me stand like this, and I held my hands out with heavy masses here. I was rotating with some angular speed omega. Let me call this omega 1. So, my angular momentum L, as we just derived, was I1 omega 1. As soon as I brought these masses in, I changed to I2, which was I1 minus, let us say, roughly 2 m L square, where m is the mass of each of these and L may be the length of my arm. But however, there is no external torque. This platform is nearly frictionless, and therefore, angular momentum must be conserved. So, nu omega, that is I2 omega 2, should be such that the angular momentum remain unchanged. After all, when I am moving my arms in or out, the other forces that are being applied by my joints are internal to the system, and therefore, omega 2 becomes I1 omega 1 over I1 minus 2 ml square. As soon as I stretch them out, it again slows down. So, this shows you the effect of change of mass on moment of inertia, change of distance on moment of inertia, and a consequence of the conservation of angular momentum. Now, I take another demonstration in which I will take this bicycle wheel, which I can rotate by my hand. If I give it this rotation, it acquires an angular momentum in the positive z direction if I take this to be the z direction. Let us see what happens if I stand on this platform and give it a rotation. Oh, I start moving. As soon as I stop it, I also stop. Let me give it the rotation the other way. I start moving the other way. Let me stop it and I stop. Let me give it the rotation this way. Stop. Let me give it the rotation the other way. I move this way. Let us try to understand this as to what is happening. What is happening here is that I am standing on this platform, holding this wheel. As soon as I give it a rotation like this, it has gained an angular momentum L in this direction. However, when I apply the force, considering myself and the wheel as the system, there is no external torque on the system. After all, this platform is frictionless. So, I and the wheel with me should start rotating in such a way as to develop an angular momentum in the opposite direction of exactly the same magnitude, so that the net angular momentum remains 0, and therefore, my body starts rotating the other way. Let me show it to you again. I took this wheel, I stood on the platform, 0 angular momentum. As soon as I give it a rotation in this direction, I start moving the other way. As soon as I stop it, I also stop. I'll rotate it the other way, and then I start rotating the other way. This is a manifestation of the conservation of angular momentum. As a third example of angular momentum conservation, and through this I also wish to show the vector nature of angular momentum, is I take this wheel, stand on the platform, give it a rotation in one direction, I stand on the wheel, and suddenly I'll turn the wheel the other way. That means initially the angular momentum that the wheel has is in this direction. All of a sudden what I'll do is I'll hold it pointing downwards, so that the L would now change direction. If L is a vector quantity and it changes direction like this, the net change in L would be 2 the initial, let me call this L0, 2L0. However, there can be no change in the angular momentum because there is no external torque, and therefore I should start rotating in such a manner that the net angular momentum change is 0. That means I should rotate maybe the other way to keep the angular momentum change 0. Let us see if that really happens. So I'll take this wheel which is rotating, stand on the platform. Right now I'm stationary. I'll turn this, and you see I start rotating. I'll turn this back, I stop. I'll turn this again, and I'll start rotating. Let me show it to you more clearly by rotating it faster. I stand here, I turn this, I start rotating. I turn this back, I stop. So this is again a manifestation of the conservation of angular momentum. An effect I would like to show you in this is, if I hold this farther away from the body and then tilt it, or keep it near my body and tilt it, there would be a difference. Hopefully it will be visible to you on the camera, and that I would like you to think about. I'll hold it near my body and tilt it. You see the speed. I'll now hold it farther away from my body and tilt it. When is it that I should be expecting to move faster, and when is it then I should be expecting to be moving slower? See it again. Hold it near, tilt it, then again give it the speed, hold it far and tilt it. It is really that I am moving the center of mass of the wheel farther and bringing it nearer by holding it farther and nearer, and that makes a difference in my rotation speed when I tilt it. So let us try to analyze what happened. When I was holding this wheel, let its moment of inertia be I, wheel, let it move with the speed omega s, let its mass be m, and let the length of my arms be L, and I was holding it on the platform. When I tilted it, so initial momentum L initial was I wheel times omega s, L final is going to be minus I wheel omega s, because I have tilted it like this. Therefore, I have to start moving. Let my own moment of inertia be I, plus there will be a moment of inertia of the wheel ml square, or you can say that the moment of the angular momentum of the wheel is angular momentum of its center of mass plus angular momentum of it about its center of mass plus my own angular momentum, and therefore that gives me minus I wheel omega s plus I plus ml square omega equals I wheel omega s, or omega with which I move is equal to 2 I wheel omega s over my own moment of inertia plus m l square from the conservation of angular momentum. Let me also try to understand, when I took this demonstration of having two masses far out and pulled them in, why did I start rotating faster? Can I understand this in terms of Newton's laws? Certainly yes. You see, when the hands are stretched out, they are moving with a speed, let us say omega L. As I bring my arms in, the speed goes down because the length or the distance from the axis of rotation has gone down. I have to apply a force on the masses to slow them down. In the process, masses apply force on me to speed me up. The balance gives me the final angular momentum, but you see, doing it this way is slightly more involved, and therefore the conservation of angular momentum comes in handy to solve this problem.